right, let's move on to section 12.2. And here we'll start with a broader sense of the overview of the hypothesis test procedure and the steps you might take to perform it. So remember, a hypothesis test is a statistical procedure to decide if the given hypothesis is true or false. This procedure usually will involve the following elements. First, we'll have to state the null and alternative hypotheses, and we'll also need to specify the risk level associated with the test. We call this risk level alpha. Next, we'll use the sampling distribution of the appropriate test statistic to determine the rejection region of size alpha. Then we'll compute the test statistic based upon the sample data, and we'll compare the test statistic to the rejection region. We'll look to see if the test statistic lies in the rejection region or not, and then based upon that, we'll make our decision. In particular, if the test statistic lies in the rejection region, then we will reject the null hypothesis in favor of the alternative hypothesis. If the test statistic does not lie in the rejection region, then we will fail to reject the null hypothesis. It's also worth knowing that if we choose not to use a rejection region to help us make our decision, there's an alternative approach we might use that makes use of something called a p-value. And a p-value is a probability that will compute based upon the test statistic. Anytime we make a decision near the end of a hypothesis test, we run the risk of making an error in our decision. So let's consider what those errors could potentially be. I'm going to start off with a null hypothesis, and it's either true or it's false. And then I'm going to make a decision to either reject or fail to reject the null hypothesis. If it turns out that I reject the null hypothesis when it's false, then that means there's no error. If it turns out that we fail to reject the null hypothesis when it's true, then in that case there's no error as well. However, if we reject the null hypothesis when it's true, we'll call that a type 1 error. And if we fail to reject the null hypothesis when it's false, we'll call that a type 2 error. This leads to our formal definitions. Definition 12.2 states that a type 1 error is when we reject the null hypothesis when in fact it's true. This is equivalent to claiming that research findings are significant when in fact they are not. A type 2 error is when we fail to reject the null hypothesis when in fact it's false. This is equivalent to failing to realize the significance of research findings. While these formal definitions are all well and good, you may still feel a little uncertain as to what these refer to. So we'll consider an example that will allow us to solidify these ideas, despite the fact that the particular example that we'll look at doesn't have much of a context in relation to statistics. So let's consider a jury trial. In the United States, the defendant is assumed to be innocent until he or she is proven to be guilty. Since the current belief is that the defendant is innocent, this becomes our null hypothesis. And we'll define our alternative hypothesis to be that the defendant is guilty. It's up to the jury to decide on the innocence or the guilt of the defendant, so let's consider the following two scenarios. In decision 1, there is not enough evidence to rule out the innocence of the defendant. Therefore, the defendant goes free. Making this decision could lead to the possible error that a guilty person is set free. In decision 2, there is enough evidence to suggest that the defendant is guilty, therefore the defendant is sent to prison or suffers some other kind of punishment. Making this decision could lead to the possible error that an innocent person is sent to prison while the guilty person remains free and unpunished. Upon further reflection, we can see that the possible error that can result from the jury making the second choice may be considered a more serious error. In the first instance, a guilty person is set free, but in the second, an innocent person is wrongly imprisoned while the guilty party remains unpunished. Let's put this example into the context of type 1 and type 2 errors, and that will help us determine which is worse in the context of our formal definitions of type 1 versus type 2. So we'll revisit the formal definition of the type 1 and type 2 errors, and you'll notice that I've made an addition of parenthetical remarks that relate back to the previous example. In this case, we can now see that type 1 error is equivalent to sending that innocent person to jail while the guilty person goes free, while a type 2 error is equivalent to letting a guilty person go free. So we can see that a type 1 error is considered more egregious than a type 2 error. Typically, since we consider type 1 errors more serious, we try to control type 1 errors by attempting to keep the probability of the occurrence of a type 1 error to less than 5%. Now that 5% is a general convention, and really depending upon the kind of test that you're performing, that might be a more flexible value. But in general, if a type 1 error has a probability of occurring less than 5%, then we're pretty happy with that. Now, at the same time, we want to try to keep type 2 errors as small as possible. So to that end, what we'll do is we will let alpha represent the probability of a type 1 error, and we're going to let beta represent the probability of a type 2 error. It's worth noting, though, that this alpha is the same alpha that was mentioned earlier when we were discussing the overview of the hypothesis test. The alpha is also known as our significance or our risk level associated with the test.